Okay, I think we'll get started here. Welcome to the Acoustics Primer webinar. This is hosted by designingsound.org, but it is being presented by Dennis Foley of Acoustic Fields. And with that, actually, let me start that over. Just, I need to actually start the recording here. Oh, they don't allow the recording anymore. Interesting. Well, then you people make out pretty well, because you're the only ones here who get to see the whole thing. I'm going to hand it over to Dennis, who is going to take us through this presentation.
My name is Dennis Foley. I'm a product designer for Acoustic Fields. I've been an engineer in acoustics for the last 30 years. My prototypes in the beginning for low-frequency absorption were featured in Electric Ladyland Studios in New York, Sony Music, New York. Mark Levinson, Cello Music and Film, has used my product extensively, and Saltine Studios in Mesa, Arizona, they just got a big write-up. And it really came to a head for me in the 90s when I joined forces with a bunch of real estate developers, and they were building commercial office space. Now, it was very high-end commercial office space. So they wanted stuff to sound really good, and they had money, and we had dollars to work with. So I took 8 guys, and we spent 8 years, and we built 114 rooms, and that forms the basis, our database that we use to develop our products. And our primary concern was speech and music intelligibility in small rooms, and this is the reason that we came up with the technologies that we have today. Our two basic technologies are low-frequency absorption and middle and high-frequency absorption. And we do that with charcoal, which is a very unique and powerful sound-absorbing ingredient, especially when you put it inside something else. It has a high degree of porosity, and it absorbs energy like I've never seen before. It's quite an amazing technology, but you can review all that on our website. We won't spend time on that today, but it's good reading, and you'll get some good information from it. Our foam technology is very unique. We have 3 thicknesses, and we focus on the 125 to 250 hertz range, which to me, based on our data of 8 years, is the most important when it comes to vocals and music. Everybody gets it right after 500 cycles, but getting it right from 250 on down, that's the real trick, and we think we've accomplished that. The carbon and the foam, first 2 of 11 products we have scheduled over the next 3 or 4 years based on this carbon technology. I wanted to make this presentation really simple because acoustics is complicated and it can drive you insane sometimes. So I've discovered in our 8 years of research, building in these rooms and testing them, that all of our energy and all of our problems is focused on just really 2 areas. And the first one is waves, and the second one is rays. Now, let's talk about the basis for all of this. Nikola Tesla was a great guy. You can read about what he did. If you're using alternating current in your life, you can thank him for it. He was a revolutionary and engineer, and he worked for the Edison Company. He worked for the Westinghouse Company, and then finally formed his own company. But he said, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. And nothing could be further or closer to the truth than that. All right, let's do a little definition. Now, I know when I say that waves are all energy below 100 cycles, people are going to say, well, then, I've seen it using different numbers, and that's true. But for sake of this discussion and illustrating these points, let's just work all of us together on everything less than 100 cycles. So waves are really long energies. They have a height, width, and a length. Let's look at a 30 hertz wave. It's 37 feet long. I mean, this is a huge, huge massive energy that we have to deal with. And when we put it inside of a box, which is basically what we're doing in a room, then we have all kinds of problems. When you think of waves, think about the ocean. Think about movement, and that'll help you kind of visualize what a wave is inside of a room. You've seen those bottles or those glass cages that people have on their desk that rotate up and down and the water moves from side to side. Well, that's a good way to visualize a wave. Now, the rays are just the opposite. They go from 100 cycles and up. They're shorter in length, and we can know that a 1100 hertz wave is only 1 foot. So a 1 foot wave, yeah, that fits in our rooms pretty well. We're not too worried about that. When you think of rays, think of sunshine. They're light rays, but they're all rays, and they're all the different forms of energy. All right, when we're in a room and we have a 30 cycle wave that's 37 foot long, and most of us are not fortunate enough to have a room that's 37 foot long. So our dimensions of the room are smaller than the length of the waves that we're trying to produce. So they're too long for the room. When this happens, the wave, I call it, gets upset. There's other words you could use, but it builds up because it wants out. It doesn't want to be there, so it builds up in certain positions in the room depending on the room dimensions. And those particular areas of the room start to produce sonic distortions. Length for waves is our biggest problem and our biggest concern when it comes to room acoustics, especially small room acoustics. How do we deal with the calculation of finding the length of a wave? Well, it's pretty easy. We just take the speed of sound. Let's round it to 1100. Let's make it easy. I don't want to get a lot of math going here. But if we divide it by the frequency we're trying to find, 100 hertz in this example that's on the screen, you can see that the length of that ray is about a foot. Okay? Let's look at some other calculations. Look at 20 cycles. Long, long wave, 55 feet. 30 cycles, which we went over, around 37 feet. 40, 27 and a half feet. So unless we have a room that can accommodate those dimensions of length of wave, then we have issues. And those issues can cause all kinds of things. Now, I want to think in terms of an ideal room. So what would an ideal room be? If we have a 30 hertz wave, and that's the lowest amount of energy our sources in this room are going to produce, then what are we going to do in terms of room dimensions to make sure we don't have any issues? Well, the first thing we can do is make every dimension longer than our lowest frequency that we will have to deal with in the room. Okay, well, wouldn't it be nice to have a room that's 40 by 40 by 40, even though it is a cube? Because that's what, 64,000 cubic feet? So that would be a nice room to have. So in an ideal situation, the wave needs its full length to run without running into anything, so it doesn't produce distortions. Well, unfortunately, we don't have rooms that are 40 feet long, most of us. If you do, you're really lucky. So we're always compromising. It's always a compromise with waves and low-frequency energy and small room acoustics. It's always a compromise from this ideal situation. And there is no 100% solution, only management. You'll never, in a 20-foot room, get to sonically act like it's 40. All you can do is manage the issues that those longer wavelengths produce. And here we have that old 30 hertz wave again running full length in the room, and you can see that it'll fit and it'll exist within the room without causing us any pressure variances or other things that can be compromised when the wave is not happy in the dimensions that it works with. Now, ideally, every room dimension should be equal in length to accommodate, or I'm sorry, not equal in length, but greater than the length of the lowest wave that you are going to produce in the room. Well, there again, how many of us are fortunate to have rooms that are that big? When they don't fit, okay, here's what happens. We get pressure areas within the room. These can have plus 10 dB, plus 15. I've even seen plus 20 of exaggeration in the frequency response. And they can be all throughout the room. They're, again, dimensionally dependent. Depending on the size of the room, these pressure areas will be in different locations. Here's another weird thing about these pressure areas is they have their own bandwidth. So they have lots of energy, and it's fairly predictable, but these are like entities of their own. Okay, they'll either smother or completely cover certain frequencies, or they'll boost and exaggerate. And we've all had those experiences in our rooms. And the total response of the room is made up of all those modal responses. So they must be dealt with. We must get them under control or managed. Because, like we said, they each have their own bandwidth, so they have lots of pressure. And the pressure varies throughout the mode. So you can see here, against the wall, our pressure is the highest. As we move away from the room boundary surfaces, the pressure diminishes. In the center, left and right of the room, we don't have any. So there's all kinds of things that you need to be aware of when the waves in your room don't fit. Let's take a microphone. I don't know if you can see this. It's hard for me to see sometimes, but there's little microphones in there, and the round black circles are heads representing a listening position. So if you're listening in a zero pressure area versus listening in a pressure area of 1, like just directly below the E at the top, you're going to hear vastly different things. You're going to hear some things. You're not going to hear other frequencies. You're going to hear more of other frequencies and not of something else. So these are very powerful things, and they're frequency dependent. Bass boom is a good example of all those things that we've heard those pressure areas produce. Okay, let's look at rays. As we said, it's energy greater than 100 cycles. They're shorter, and they move everywhere in the room. They reflect off of everything. Consoles, furniture, walls, ceilings, floors. Any room object will produce a reflection. So you have all of these reflections. Let's just focus on 3, because I think that'll help you understand what needs to be done in terms of your small rooms, no matter what the usage. If it's playback, if it's recording, if it's monitoring, these are lateral reflections, these 3 that we're going to talk about right now, and they're really the most important. They have about 85% of the data that we work with as mixing engineers, as acoustical engineers. They really have the data. Now, there's other reflections that we have to deal with, but I think for the sake of this, to illustrate how important reflections are, let's stay focused on just these lateral reflections. Okay. There's lots of sonic data in these 3 reflections, and that's what we have to look at. Now, these are the sidewall reflections, the left wall and the right wall. So let's put ourselves between the left wall and the right wall, wall and realize that we have two walls, one for our right ear, one for our left ear. There's lots of sonic data in these three reflections that we're going to talk about, okay? Let's first examine what the direct sound is. We've all seen this. We've all heard this. It's the direct energy from our loudspeakers. It's that straight line, short path, very little room sound. It's near field most of the time for us. We sit near field so that we get more direct energy and not room sound. So let's focus on the first sidewall reflection, and that's off the right and the left wall. That's that first reflection that hits the wall after our direct sound, okay? Now what happens? Well, it travels a longer distance. So what are we going to have? We're going to have two things. We're going to have room sound, because I always say this to people. I said sound takes on the characteristics of the surface that it strikes. So for sake of discussion here, we'll just call that room sound. So the room sound is time delayed in comparison to the direct sound, which is the wanted sound from our speakers, okay? Don't forget that word time delay, because that's the critical factor in understanding reflections, okay? Secondary reflection is when that primary reflection travels across the room and strikes the other wall. So now we have a right wall and that reflection hitting the left wall. So we have that mixing with the direct sound, thus striking two surfaces. We have more room sound, and both are time delayed when we compare them to the direct. Okay, the third one is side, side, side. Great amplitude loss on this one, much more room sound, and now we're creating a virtual image. So we have the image from our direct sound, and we have the image from the reflected sound. And the image from the reflected sound is time delayed. So we definitely want less of that, okay? Now here's why. In that reflection, there's a lot of things going on, and it took me 3-4 years to figure this out and really get a handle on it, because in our electronic mixing and manipulation of our signal with electronics, we can, shift from left channel to right channel. We can center the image in the middle. But we do all that electronically, and we have control over the knobs and the buttons that move that signal around. Well, here's the room doing the same thing, okay? So you have your room doing the same thing, basically, that you're doing electronically. Well, we don't want that, obviously. We want the room to get out of the way, and we don't want any shifting. We don't want any spreading. We don't want any spaciousness or air or any image effects added to what we're listening to. Well, the room does that. It will produce those things, and they're in the reflections, and they're in the time. If you see the left indice on the chart, you see the time delay. You see the level, and then the bottom, you see the time delay. So you can see that there's a really narrow band where a lot of different things go on, okay? Well, what's the bottom line to all of this? We have to control reflections. There's many, many ways to do it, but I want you to realize that that reflected energy needs to be dealt with, because it has a lot of information in it that's only confusing to us. So we have to treat it. We have to use it correctly, and definitely have to respect it. All right, so let's just do a quick summary here. Waves cause about 75% of our room acoustic issues. Those are the frequencies below 100 cycles. Room modes, they're very powerful. They produce unwanted pressure areas which can blur and cover and smear our energies. The reflections mix with our direct sound. They contain certain sonic information. Reflections contain a lot of data, which we just went over. Image shifting, spaciousness, timbre. So when we add these two together, waves and rays, we get what's called room distortions, okay? Now, room distortions are four main types. I've tried to break these down into four general areas so it's a little bit easier to understand. These are the four audible room distortions that waves and rays produce. First one, room modes. Everybody knows what those are. We've touched on them a little bit. When a wave doesn't fit in the room, we get a pressure buildup based on the dimensions of the room, and that's called a room mode. They're frequency dependent. They have their own bandwidth. They're just nasty creatures, you know. So I don't like them at all. In fact, I hate them, so that's why I invented the technology that I did. Speaker boundary interference. That's the second one. That's the interference that comes in that little space between your speaker and the closest room boundary surface. Comb filtering is that area also, with a repeated amount of energy going back and forth, trapped between the object and the wall. And then fourthly, poor diffusion. That's really the fourth room distortion that we'll focus on today, and that'll give you a pretty good idea of the main four. Excuse me for a minute. Okay, room modes. The energy that gets trapped between two parallel surfaces are called axial modes. They're the most powerful. 4 surfaces, tangential, and 6 surfaces, oblique. I don't want to go into each one of them individually. There's no need. I think for purposes of this, we'll be able to understand room modes in general as room distortions and go from there. Here's the thing about room modes that drives me insane, is they have their frequency of resonance, and they also have fundamentals throughout the room. So not only do you have to deal with them, you have to deal with their cousins. That's more issues to be concerned about. They have areas of high pressure. They have areas of low pressure. They're opposite polarity. They're increasing on one side, decreasing on the other side of the wave. And the whole room response, like we stated before, is made up of all of these modes. And each mode, obviously, we talked about that, has its own bandwidth. All right, speaker boundary interference. I see this so much, and people just don't seem to hear it. I hear it immediately when I walk into somebody's room. The distance between the speaker and the first boundary that's closest to it, which usually is the side wall, is very, very critical to get right. It has such a big impact on the frequency response that you're going to hear at the listening or monitoring position that a 1-inch movement either way can be critical. So you really need to make sure that that distance between the speaker and the room structure itself is right for the room size, okay? Because if it isn't, then the distance between those two is going to form, the energy that gets trapped between the speaker and the wall is going to form another image. Now, you don't have to take my word for this. Just next time you're playing your system, stand between your speaker and the wall. You'll hear it. It's there. You may not hear it at the listening position, but you will hear it there. And those virtual images, as we know from the past, will combine with our direct sound. So we have this little area of images partying over here to the side of our speakers that we have to kind of get a handle on too. They can enhance or cancel direct sound depending on their amplitude and phase. Okay, so we need to really be concerned about these areas. These are critical areas. These things, one of these things we're discussing by themselves, probably not that great of a deal. But in a small room, you've got a bunch of these little things that when you add them together and they accumulate into a lump sum, then you've got audible distortions. And the goal of our rooms is not to add any distortions, hopefully. All right, comb filtering. This got its name because on a graph, if you measure it in a room, it has little teeth that look like the teeth of a comb. So that's how it gets its name, comb filtering. It's a direct versus reflected energy thing. It's a reflection. It causes time delays. It's a continual reflection over time. It's just not immediate. It carries on over time. Now, it's a short amount of time, but nonetheless, it does carry on. So when it does that, we get image and timbre distortion, and we definitely don't need that. It can occur between our consoles, our walls, the speaker, the wall. It can be all throughout the room. It's mainly in the front part of the room where your energy-producing sources are. Poor diffusion. This is a real big problem in rooms. It's either too dead, the walls don't have any objects on them to provide any natural diffusion. We need a certain amount of spreading out of energy. Rooms get too dead, they absorb too much energy, and it's not realistic. So we have to make sure that we have diffusion. In a control room or a mixing room, it used to be very popular to put both vertical and horizontal diffusion on the rear wall of a control room. Well, that was the thinking at the time, probably 10 years ago. Now, it's mostly just vertical diffusion because they realize that it's diffusion in the horizontal plane, which is the most important, like our lateral reflections. So a room has to have some kind of diffusion. So we need to keep that in mind when we're working with our rooms. Okay, well, this went a little bit faster than I thought, but anyway, when we think about Tesla again, and he would have loved this last slide presentation, which I'm going to show you, because he would have just appreciated this. I found this on the internet a couple days ago, but these guys took a plate and they hooked it to a generator. And on the plate they put salt. And some of you have probably seen this. And then they went ahead and turned the generator on, and look what the plate looks like at 345 cycles. So we're beginning to see a little bit of waves. Okay? So what do we see about going a little faster? Look at this at a little over 1,000. Okay, more. 1820. 2000. 3240. Remember, waves or rays are shorter in length, and there's much more. Look at this. 3835. Almost 4,000. Look at that. Okay, well, this went a little faster than I thought. This is my first webinar, so you'll have to bear with me, but we'll have another one August 20th where we'll take this information, review it a little bit, and then we'll go to the application of absorption and diffusion technologies and how it affects the signal in the room. So thank you so much. I have to work on my length a little bit more.
Any questions? Dennis, I'm assuming it's okay for us to share a copy of the PDF on the website?
Absolutely.
Okay, so the slides will be up in a few days on designingsound.org. Hopefully Dom's recording is going well, and we'll make that available as well if he gets that to us. Any other questions for Dennis before we close up this meeting for today? Okay.
Well, thank you all. Thank you all very much for your comments. I'm just seeing them on the screen. You're all very welcome, and I'll definitely do a little bit longer next time. Thanks again.
And thank you, Dennis. It doesn't seem like anyone's got any questions, so we'll close this up, and hopefully we'll see each of you in about a month when we do the second part of this acoustics discussion.